Welcome back guys, my name is Abram Mahoy, and on this video I'll be taking you through linked list. So those who are new to linked list, I'll be taking you through to understand what linked list is and then when is it being used. So as you can see, we do have nodes on which this thing kind of represents this thing, on which it contains what? A value, and then a node on which is pointing to. So the node that will be stored in this node, it will be this thing, and then the node that will be stored in this node will be this thing. What I'm trying to say is that nodes are pointing to other objects. It can be no object, or it has to be a type of node. So for example, this one is pointing to null, meaning it is not pointing to a type of node. But when we create a node contains what? An object on which can be a string, an integer, anything, or other type of object that you have created. And then it also has to have a type of node on which is pointing to. Basically what I'm trying to say is that a single linked list is about linking objects to one another. It can be, for an example, let me give you an example. If you take a picture using your phone, the picture that you took previously is being linked to the upcoming one that you're going to take. Meaning from the current picture, you can access the previous one and the next one. Hope that one makes sense. So let's jump to the next part, on which now I'll be explaining to you. We do have different types of linked list. We have a single linked list, secular single linked list, and then double linked list, and also a secular double linked list. So let's start with the single linked list. So what's happening is that this is just one direction. This object is pointing to this object, and then this object cannot access this object, but this object can access this object. So it's pointing to the same direction. This object can access this object, but this object can never access this object. Hope that one makes sense. So let's go to secular single linked list. This object is pointing to the next object. Same applies to the previous one. This object can never access this object. And at the last part, the reason why we call it secular is because this node is pointing to the beginning of this list, meaning you can go in secular. Let's come to a double linked list. At first we said this object can't reference this object, meaning we cannot get this object if we have this object. But in this situation, this object can reference this object. Hope that one makes sense. And this object can reference, it's bidirectional. Objects can reference each other, but this object cannot access this object. You have to traverse from here to here to get to this node. And then with secular double linked list, what is happening is that this object can access this object, and this object can access this object, and also this object can access this object. Might be a bit confusing, but I'll be jumping straight to code. We're going to be creating our project, just a simple console application, on which in this case I'll just be demonstrating a single linked list only. Yeah. So but I'll be creating different nodes for all of this one so that you understand, because the logic is almost the same basically. So let's say this video is basically on single linked list, just to give you an understanding of what's happening. So okay, I do have an empty folder here on which is called data structures. So this is where I'm going to be creating most of the data structures. So let's create a new folder called single linked list. So this is where we're going to be creating our single linked list, and then now we're going to be opening our terminal to create our project. So specify the framework on which you're going to be using. Let's open up Visual Studio Code. Okay, so we do have our program trust. So this is where we're going to be creating this thing. So now let's start the work. Let's wait for our C# extension to give us those assets. Yes. Okay, now let's start. So we're going to be creating our class called node, on which basically this is this thing. We're going to be creating this thing because this thing is this thing, right? So we're gonna be, in this case, I'm gonna be creating a node on which in this case, node will be containing objects of type string. So let's do that. I'm just gonna call it value. So I'm just okay. So let me write that. So public string and then public node on which is next, on which this is the type of object on which it is referencing to or pointing to. Okay, cool. So let's do some get and set. So it's easy for us to. Same applies to this thing. Okay, so now let's create our single linked list, on which our single linked list contains what? A node on which is this one, this one, and this one. But at first, as I said, we need to have this thing to access this thing, and then from this thing we can access this thing. So when we create a linked list, we do have something called a head, in which this is going to be referred to as what? As head. And it's always best to what? Also keep track of what? It is also best to keep track of what? Of the tail, on which is the last element, on which doesn't have any node that is referenced to. And it's also best to what? To keep track of what? The number of elements on this linked list, on which you're going to call that variable what? Count. So let's move on to this thing. So we're going to be creating a region called count, right? And then we're going to be also creating what? Our head, which is of type node. Okay. And then we also have another node called what? Tail. Let's make this thing public so that we can access them here, right? Also, let's make our class public. Okay, cool. So public class, there's some error here. Okay, so we forgot to make this public. Okay, that's great. So now we're going to be moving to the functions. So at first, a linked list has no head, it has no, meaning it's empty. So the first of all, we need to know how to create. We need to create some operations of inserting and then deleting and then inserting at a specific position. So let me list all of them here. So the first one we need is what? Just a normal insert, right? And then the second one will be what? You can say insert add, and then the third one will be insert add first, and then also insert add first, and then also we're gonna be doing something called insert at last. And this one is going to be inserting at the last element. So let's do all these 4 operations. Okay, let's do what that's the one, which is I don't know whether we should create all of them. I don't know. I don't want to make this video too long. Let's make insert add. Let's remove this insert add first and all this. And also let's create another one called delete. Delete add. Yeah, on which you have to specify the position on which you want to delete it. So these are the 4 operations that we're going to make our linked list use. We can insert a node on which automatically will insert at the last. Insert add, we can specify the position within the linked list on which we want to push our new node. And then also we have delete add, on which we specify the position on which we want to delete the node. Keeping in mind that we do have a count, on which it will tell us, we will use count in order to make sure that the person is deleting a node on which it exists within the collection, not within the list. So we do have 3 operations that we're going to be creating. So we're going to be creating the first one will be insert, on which we have to provide a new I've just called it a new node. And then this thing will just check if count is equal to 0. Okay, we forgot to do something. Within the constructor of this thing, when you create a single linked list, the first thing we need a single linked list. We need what? We need to make sure that the count is equal to 0. And then if count is equal to 0, we're just gonna make sure that the head is equal to tail. And then the head is equal to what? New node. And also our tail is equal to new node. And then let's increase our count. This is it. And then let's just return this thing so that we don't have to go down. So now we do know that when we insert, we're going to check if however there's elements within this thing. And then if there are no elements within this thing, then that's when we're going to move on to the next phase. So now let's move on to the next part, on which, what if there are elements within this thing? So we do know that we do have a tail, on which a tail we expect it to be pointing to the last element, right? So at this point, we need to make sure that our tail is pointing to something new, and then assign our tail to that thing. So we're gonna be tail is equals to, okay, tail on next is equals to new node, and then new node, and then tail is equals to new node. And then as always, you're gonna have to do what? Some count. Let's increment our count. This is it about insert. Then we're gonna be creating insert add, on which now we specify the position on which one inserted. So first of all, before we go any further, we have to make sure that this person inserted a position on which it is at least between the range, like it doesn't give us out of index exception, right? So now we're gonna do like this. We're gonna say if count is less than, okay, for example, let's say we do have 3. Okay, let me go through this thing. So in this case, we do have 3 objects on which when we insert this one, our count is going to be 1, 2, and 3, right? If we insert at, we can only allow what? Insert at 4. You can insert at 4. You can insert at 0, but you cannot insert at -1. You cannot insert at number of count plus 2. Hope it makes sense, because you don't have an object. That one will be out of index. Okay, yeah. So first of all, we have to do from if position, we have to say if position is less than what? Is less than 0 or what? If position is greater than count plus 1. Then let's give this person something. Let's just say not that. So, okay, let's say exception. Okay, let's just say index too big. Let's not need it. Alright, and as always, let's return this thing. And then at this point, we do know that this person is providing a specific index. So let's go back to this thing. So since we do have a list here, the question is, what if this person wants to insert at position 1? Because like a normal user wouldn't want to insert at position 0. We expect this thing to be at position 1. Okay, so that means this case we should say less than 1. Yeah, should make sense. So if this person says they want insert at position 1, meaning they're inserting it first, basically. So we're gonna be pushing this thing here. So let me think. Okay, so let's see if we can do that. So if count, if position is equals to 1, and this person is inserting. So we're going to say what? New node. Okay, we need to create what? We need to get our head. Okay, let's create a node called current, which is we pointing to head. And then we're gonna say okay, insert add, we also need to provide the node that we're trying to insert. Hope that one makes sense. So we're gonna say what? New node next is equals to current, on which basically is the head. And then okay, let me just for simplicity, let me just create head and what? Our head is equals to new node. That one also makes sense. So meaning we are able to insert at the beginning of this thing. So what if we want to insert at the end, right? So okay, so inserting at end and the middle, I feel like it's based on the same operation basically, because let me see, if we want to insert at position 2, what we're gonna do, we have to stop here so that we make sure that the point is pointing to a new node. And the same applies to this thing. If one is at position 3, we have to pause here. So okay, let me go back here. So we say if we want to insert in position 2, we have to make sure our current node is pointing to this one. It makes sense, right? So we can use this thing using, we can go through this thing using, we can say current index, which is equal to 1, and then we're gonna say blank current index is not, it's not equals to what? It's not equals to position. Current index is not, it's not equals to position. Okay, it's not equals to position minus 1, because that's what we are trying to get here, right? So this will be our position, which is 2. So we want to stop here, right? So meaning this thing should be at, okay, let's see, I feel so. So now we know that once we get out of this thing, so okay, so what we're gonna do is just gonna be incrementing our current, and then meaning once we exit this thing, we are pointing exactly at the node that we need. Then from there, what we're gonna do is just gonna say, so since we are inserting within them between 2 nodes, so what we need, this will be our new node, right? I'll just say new. So the best way to point into this thing is to make sure that this pointer, the point of this thing, is pointing to the same thing as this thing. Let me delete this. Alright, and then from then we're gonna be moving what? We're gonna be moving this pointer to point to this thing, so that we don't lose this object. Because if however we do it otherwise, let me show you. So if however we do something like this, we move our pointer to point to this thing, that means we lost all these remaining objects. Because this thing was supposed to point to this thing, but now it's pointing to this thing, on which this thing automatically points to nothing. So the best operation to do, I lost that thing. The best operation to do, new node, is to make sure that this thing is pointing to the same thing that there is pointing to the same thing as what? As the head, and then from then we're gonna be shifting our head pointer to be pointing to this thing. So now it's going proper. So now we're gonna be doing of like head. So we're gonna say new node dot next is equals to head dot next, and then our head dot next is equals to not head though, but current. So So as we are increasing this thing, we have to make sure that we also update our current is equals to current.next, and then head.next is equals to what? New node, not head.next but current is equals to a new node. So we're going to be creating some simple tests to make sure that this thing works. So we're going to be starting at inside and all that thing. So now we're going to be creating some small things. So let's create our single list. Single list, which is going to be, and then from this thing, from cell.insert, on which now it's going to be inserting anyway. Okay, so now we need to create our new node. Let's create those nodes A, B, and C, right? So we're gonna be creating our new node. Let me call it A, which is supposed to be new node. And then since I provided A, I can just provide the value, which is A, so it'll be what? It's a string. And then okay, let's create these objects first. And then node. Okay, yeah. So we do have a node on which this node is not pointing to anything since it's the first node. So now let's provide this A. Let's see if we'll be able to do this thing. I'm gonna be debugging this thing so that we see it properly. I'm gonna be putting a breakpoint here. Let's see what's happening. Okay, in the meantime, let me create another node. And then the value will be what? Okay, so now it's good. Let's wait for our debug to finish. So another node called C, which is supposed to be node. Okay, I don't know what's happening here. Let's try it again. Seems like there was some bug because it never hit our breakpoint. Or was it because we still kept on writing code? Okay, yeah, so our breakpoint has been hit. So now here, I hope you can see. Okay, so now we're going to be creating our single list. We're going to be creating our node. So on which our SLL, our count is equal to 0, our head is equal to null, and our tail is equal to null. So let's check at the insert. So when we insert this thing, our count increases, and then the head is equal to 8, and same applies to the tail is equal to 8. It's equal to 8. So meaning the insert works perfectly fine. Let's stop our thing. So now we're gonna be doing something like this. So we're gonna press insert. We're gonna be inserting 1B now. Let's see if this thing. Let's just put it here. Let's debug. See if however these things will be linked. From this, we should access this. Okay, fine. So our SLL is count is equal to 0, that's equal to 1, that means A, head is A, and also tail is equal to A. So now let's move to the next one. So now we can see that the tail is P, but our head is still A. Meaning now, let me show you something. Let me close my tail. So we do have this head, right? This head should be pointing to what? To tail, on which our next is equal to P, on which our insert is working perfectly fine. Now we're going to be doing our insert add. So insert add, we have to specify what the position first, on which let's say 5. We do have what? How many items at this point? Only 1. So meaning we should be inserting at position 1 and positioning 2, and also position 1 itself actually. So let's try with let's say -1. Let's see what's going to happen. We're just trying to test if this thing works proper. When we do have insert, okay, let's see our thing. Our head and tail are almost the same, and then index is too high. Okay. I just say index. Let me just say index not valid. Yeah. So now we are good to go. Okay. So we do have insert add. Okay, that's good. For me, it's good. So let's try with, let's say 4. Should be throwing the same thing basically. Okay, index not valid. That's good. Okay, so we do know that our insert. Okay, let's try to insert position 1. Let's see what's gonna happen. Let's debug again, see what's gonna happen. Okay, so let's insert the position 1. Okay, it did not work. That one did not work. So it said our head became B, on which it was good because that's what was supposed to happen since we're inserting at the beginning, right? And then the next is pointing to 8. That means the only thing that we did not increment is count. So meaning here we did not increment our count. Let's try it again. Our SL on which our tail is supposed to head, and then now we're inserting at the beginning. That means our new head becomes B since we're inserting at position 1. Let's provide. We do how many items we do have. Let's insert at 2. Our head and then our tail is equals to AA. So now our head is equals to A and our tail is equals to A, meaning it did not do the right thing. We haven't updated, but let's see our next. So let's close our tail. Look, our next is good, but we did not update our tail at this point. So meaning we said new node is equals to. So we need to also check something on that. Okay, so new node dot next is equals to, well, insert not head but current dot next. So let's go back to this thing. It's possible that current dot next is equals to tail, and then if that's the case, okay, wait a minute. So we might be trying to insert at this position, right? Meaning the current. Okay, let's check something. So when we insert, there's a chance when we get out of this while loop, there's a chance we could be pointing to our current. Where is it? Our current could be what? Our tail. When we have to cater for that situation, right? Because what we do is set new node the next is equals to current dot next, meaning if this is our tail, then this current dot next will be null, and then current dot next means our node will point into this thing. So we need to check something. If current is equals to tail, then what we're gonna do is we're gonna say tail is equals to new node, right? Let's try it one. This video has been going for so long, 10 minutes already. Okay, now let's step over this thing. So we have our head, we have our tail on which. So now we're trying to insert at the end, meaning our tail should also update it to be B. On which is good, our tail now becomes B, and then our head is equals to A, and then the next is equals to B. It worked perfectly fine. Also, our count became 2. Worked perfectly fine. Now let's move on to the next operations, on which will be just delete that. So let's minimize this thing. So now we're gonna be creating. So probably void delete. We specify the position. In this case, you care much about the position, and then basically it's almost the same operation as this. And then let's minimize this. If this is the case, meaning we are trying to delete the position and that is not valid, then we're just gonna be doing this thing. But otherwise, if we delete the specific index, that means you have to do the operation. So we can be deleting at the first. Let me try to see if I can. Yeah, that means if we specify 1, we're gonna be deleting at this, and then yeah. So are the operations for all of this the same? Okay, let me check something. We have. So if you let me just do it that way. If count is equals to 1, what we're gonna be doing, we're gonna be saying our head is equals to. Okay. So if this is the case, we wanna make sure our head becomes this. Yep. So once head becomes this, that means this thing automatically will be forbidden because we cannot access this object. Because when we start the linked list, we start with the head all the time. So head is equals to head next, basically. Head is equals to head next, and then now operations, I think they're gonna be the same. Does it make sense to me? If we want to delete this thing, if we set our count to 0, I feel like that one simplify the whole thing. So otherwise this will be 2, 3. So we want to stop here at the same thing as this one. So basically this is almost like insert, it's just that now we inserted, it's just that now we delete. So now let's see if we can. So we have inserted. Where's our thing? So we do have this thing. Let's minimize again. So integer current is equals to 1, while current is equals to 1 minus 1. Because if we want to delete this node, we have to stop here so that we take our pointer to point to this thing. Alright, meaning we're gonna say this thing will be pointing to the same value that this thing is pointing to. So now we are at that position. So we're gonna say current next is equals to current next. So I'm saying if I want to delete this thing, I'm saying current.next, meaning this thing will be pointing to the current.next, which is .next, which is this one. And then from there, I feel like I've done something. Here we did not decrement our count. And then now we come here, current.next, then we move to the next one. And then Will the tail be the same? In case, will the tail be the same? Let's say, for example, we want to delete this. That means our tail will still be the right one. But if we want to delete this thing, that means now it should be something like this, meaning this will become our tail. Right? So we need to make sure of that. So we need to do some exceptions. So current dot next was good. Let's do some check. Current dot next is equals to now. So basically what I'm saying is that current dot next. Okay, let's say we want to delete this one. So meaning current dot next is equals to now, right? Meaning this one was the tail. Then this question now, then we know that we are deleting what? The node, the tail I meant to say, because current dot next, because we'll be stopping at a node before the one that we want to delete. Then now current will become equal. Okay. So current will be equals to tail doesn't make sense to me. We want to delete this one, so we are stopping at this one. So current dot next, and which is this one dot next is equals to now, right? Which now this thing will be pointing to nothing. This thing will be pointing to nothing. Current is equals to tail, and then current dot next is equals to current dot next. I hope this one works. So we do need to test that one. So basically we're going to be inserting, let's just say insert. Okay, I'm supposed to just say, and then paste and functional ABC. Now let's do our SL.delete, and let's say the first position. Let's see what's going to happen. I'm just going to put our breakpoint straight here. See if our delete is going to be working perfectly fine. So we do have a counter of course 3 on which our head, the next equals to B, the next equals to C. Okay, that's good. Right, so now you want to delete what our head, meaning you want to start, we will make sure that our head becomes B. Let's do some operations. Okay, current. So we handle exceptional reference, object reference not sent to. Okay. So what is happening is that while current so here current index will be is equals to now position minus 1. Wait, if count is equals to 1, wait a minute, we were trying to delete one at 1. If position is 1, we should be coming here basically. Am I lying? No, I said if count. I made a mistake. If position. Okay, let's try it again and see what's gonna happen. Should be done with this thing like in 5 minutes. Okay, now let's move on. Let's see our answer on which our head is supposed to. Our head now becomes B, on which our next is gonna be C, and then that's it. That means deleting at the first position is good, Now let's delete that second position. We're trying to delete B. Let's restart this thing and see what's happening. So we have, okay, this is our SL. Okay, next and next. So we have ABC. So now let's delete an AC, meaning we have a head on which the head's next is equals to C, and then the count is equals to 2. Worked perfectly fine. So now let's delete that 3. So wait a minute, our tail is still C. That is good. So now let's delete the position panel on which we are deleting our tail, meaning our tail should also be upgraded, should be updated. So now let's open our SSL. I don't know why I keep saying SSL. So we do have our tail as C, and then we expect our tail to be B now. So let's keep track of this one. So we do have an exception on which okay, let's try that one. So if current.next is equals to null and current.next is equals to is equals to null. Okay, let's see something. Okay, let's see what's happening. Let's try to debug this thing properly. It's messing me up a bit. Hope we get this one. Okay, so now let's delete that 3. So if current.next, the next is equals to null, on which this is true, our current is equals to T, on which this is what we are trying to do is that we are trying to do so now we do what current.next is equals to null. So what we do is that we say current is equals to tail, meaning this is our current, tail will be here now, and then we have to make sure that this thing is pointing to null. Alright, then current.next is equals to null. Can we do this? Will it? And then we can do some else here. Now let's restart that. Okay, so now let's do our next. So our current at this point is equals to null, on which we come here. We get inside, then we set our tail to be equals to this thing. So our current.next, our current.next now becomes, wait, our current.next, wait, why did we stop? So now let me stop here. And we were supposed to stop and before. Okay, I think this is where we went wrong. Because our current now becomes what? It's equals to C, on which we stopped at the wrong one. So not equals to position. I feel like that's where we went wrong. Now let's see. Let's start this thing. So current okay, so wait a minute, current is equals to C. So are you saying -1 is pointing to So at this point we do know there's one element, and that means at this point we do know there are two elements or more. So if there are two elements within this thing, how do we deal with it? So our current index is equals to 1, and then our count here will be 2 or more. What did we say here about this y? Okay, so let's see what's happening here. So if our current dot next, do you think we should just, okay, let's see if this thing works. So we say because when it gets, that means you're pointing to the last element, which is not okay. Hope this one works. So now our current is equals to what? It's equals to B next, it's equals to C next, it's equals to none. So our current which is B is equals to T. No, I'm doing it wrong. Our tail becomes current. Let's do this thing. Our tail becomes current, and then our current to the next, which is C. In this case, we'll see. Now we make it now. So wait a minute. Let's go back to this thing. Okay, seems like it worked now. Okay, let's remove this breakpoint here. Let's debug again. Okay, so now let's go to our SLL. I'm more interested on the tail because at this point we're trying to, yeah, our tail became B. That's good, and our count also went down. But let's try to do 2 again. Let's see what's happening if we do 2. Meaning we're just going to be having A and C. A will be pointing straight to C. I want to see if it's going to work again. Our tail is equal to C. Our tail is equal to C, but our head is equal to A. On which next is pointing to C. Let's say 1. Probably this is our solution. Then that means we're done with this thing. Okay, SLL is equals to head, and then our next was to, everything is good. Our tail is supposed to C. We're trying to remove what? The first, which is our head. In which now we start what our tail is supposed to, our head is supposed to B, and then our tail is supposed to C. That means we worked. So we managed to create our single link list. So I hope you enjoyed it. Thank you for watching. Cheers.